Hello and welcome to this video on harmonics in electrical signals. For this video we're going to use a spreadsheet software such as Microsoft Excel to produce some sine waves and actually show the effects of harmonics and then how we can recognize different types of harmonics. The two types of harmonics that we're going to look at are odd and even harmonics, and we'll explain what those mean as we go. To start with though, I want to start by producing a sine wave in my document here. And to do that, I'm going to create a column for degrees. There's a 360 degrees in a sine wave. And so I want to start by going up in 10 degrees. So 0, 10, 20, and so on and so forth. What I can do here is select these degrees that I've typed so far. And just by dragging the bottom right hand corner there, I can extend this. And it should follow the same pattern of going up in 10 degrees. So I've produced a list from 0 to 360 here. If you're following along at home, you can do similar if you have Microsoft Excel or a similar sort of spreadsheet package. What we're going to do next is we're going to plot a sine wave, but there's a slight problem because Excel doesn't usually work in degrees. Excel works in radians, and so my second column here I'm going to call radians. I'll just make these headers bold as well. And so we can convert from degrees to radians very easily. There's a command in Excel to do that. Any command in Excel needs to start with an equals sign, and so the command is radians, open brackets, and we want to convert the cell to the left into radians. What I can do is just double click this little corner in the bottom right of the cell that I've completed, and it should do this for all of our values. So I've converted all of my degrees into radians here. The next step that I want to do is to plot our sine wave, and I want to call our sine wave V1. So beginning with an equals, the command for a sine function is sine, S-I-N, open brackets, and we're going to pick the radians there. And sure enough, we can complete that for the whole list. I'll just very quickly produce a graph here, a scatter graph, just to prove what we've done. So we've got a sine wave there. We're going to make some little alterations to this before we talk about harmonics. What I'm going to do first of all is I want to increase the amplitude of that sine wave. So by default, sine waves go from 0 to 1 in their amplitude. If I just bring that graph back again, we can see that here. We're going from 0 to 1 and then down to -1 and back to 0 again over the course of 360 degrees. We're going to change that. Let's say that we have an amplitude of 10. So for my function here, I want to, rather than sine of B2, or the radians in this case, I'm going to make that 10 times the sine function there. And I've only done that for the one cell, which is still going to give me a value of 0. 10 times 0 is still 0. But double clicking that corner there, I can do that for the whole lot. And so now if I plot my scatter graph, we now reach a value of 10 in amplitude. Okay, let's very quickly talk about what harmonics are, because for a variety of reasons in electrical systems, it's very difficult to transmit a pure sine wave like the one we have here. By the time it gets to the end stage of its transmission, we often find that some other signals have crept into the mix, and these are often called harmonics. Harmonics are a multiple of the frequency of the original waveform, and we'll see what that means by illustrating it with a second sine wave, and this is going to be a harmonic. So what I want to do is another sine wave. Let's say this one has an amplitude of 5. So 5 times sine, open brackets, we want our radians function again. But what I'm going to have here is the third harmonic, and we'll see what that means in just a second. But my radians are going to be multiplied by 3. So 3 times the cell containing our radian value there. And again, I'm going to copy that for the whole lot there. Let's do the same with another wave function. We'll call it V3. And we're going to say this is what's called the fifth harmonic. So again, let's say this has a smaller amplitude again. Our first had an amplitude of 10. Our second had an amplitude of 5. Let's say this one has an amplitude of 2. So 2 times sine. It's a fifth harmonic, so 5 times the radians. Now, what do we mean by these harmonics and fifths and thirds and all that kind of thing? Well, hopefully if I plot these, you'll be able to see with an example here. So let's make this a bit bigger and let's see what's going on. First of all, we have our original sine wave there. And normally this is called our fundamental. Our fundamental goes from 0 to 360 as we'd expect. But we've also plotted these harmonics V2 and V3. Let's have a look at what these represent. So V2 is in orange and we made that our third harmonic. And what you might notice with it being our third harmonic is that there's 3 complete waveforms in the space of one fundamental. So there's 3 orange waveforms there. And likewise, we plotted our fifth harmonic, which is our grey waveform here. And you can see again that there's 5 waveforms in the space of 1. We don't want to have 3 separate waveforms, however. What we've actually done is we've combined these signals in transmission. The original has kind of been mixed up with these harmonics, and so finally what I want to produce at the end here is a total. We've transmitted our V1, for instance, that was our original frequency, but V2 and V3 have kind of crept into the mix as well. And so the last column here is going to be a total, and I'm going to use the sum function to do that. So equals sum, open brackets, and I'm going to sum these 3 cells together just by adding them, just by dragging the cursor over them and add them together. And by doing that, I've actually added all 3 waveforms together. Here they were all 0, so I get a total of 0. But double clicking, and we've got a total for the whole column there. So again, what I'm going to do, same as before, I'm going to plot a result of the original combined with these harmonics added in as well. And if you're doing this at home, you simply click on the column for degrees, hold down the control or command button if you're using a Mac like me, and click on the column for the total as well. So I've highlighted both of those columns there by just clicking on the column headers. Now that I've got both of those selected, I'm going to insert a scatter graph. You'll notice that I've been selecting scatter graphs from the choice of different graph or chart types here. And the type I usually pick for these diagrams is this one, where you've got points with a smooth line. We're expecting sort of smooth curves with sine waves, so I've generally picked that one. So if we select that one, now we get our resulting graph. And this is what we call a complex wave now, because we started off with a simple wave, a sine wave, but because other harmonics have sort of crept into the mix, we get this total that gives us this very sort of unsightly waveform, and we call this a complex wave. At this point, we want to sort of look at how we might recognize whether we have what are called odd harmonics or what are called even harmonics in our waveform. What do we mean by odd and even harmonics? Well, I'm simply talking about odd and even numbers. So the second, the fourth, the sixth, the eighth, they would be examples of even harmonics. The third, fifth, seventh, ninth, they'd be examples of odd harmonics. And what we've got here is examples of odd harmonics, because we had our fundamental, we had our third, and we had our fifth. So we've got odd harmonics in there for V2 and V3. How might we recognise odd harmonics? Well, we'll get to that in just a second. It's very difficult when you're presented with a complex wave to kind of try and pick apart what were the original sine waves that have gone into it. We worked to construct this very complex wave, and we know exactly what was involved in producing it. But say you were given a complex wave, it's very difficult to kind of try and pick apart what was involved in putting that complex wave together. It's a bit like having the ingredients to a cake. You might know exactly how much flour and exactly how many eggs to mix together to make that cake, but if somebody gave you a cake and said, what were the ingredients used to make this cake, you would never exactly be able to say without reading the instructions or the label. So it's similar with our complex waves here. We've got a complex wave and we want to be able to identify not precisely which harmonics have gone into making it, but to start with at least, we can recognize whether the harmonics are odd or even. I want to illustrate this by changing our harmonics to even harmonics. We had odd harmonics here. We're going to change them to even harmonics. So I'm going to get rid of this graph just a second. I'm going to go back to our harmonics here. V1 I'm going to leave alone because that was our fundamental frequency. But V2 and V3 are both odd harmonics. I want to change them to even harmonics. So let's change that 3 to a 2. So it's not the third harmonic anymore, it's the second harmonic. And I've only changed that one cell. I need to change it for the lot of them. I'm going to double click on that little corner. It's going to update my whole list there. Same with V3. It was the fifth harmonic. Let's make it the fourth harmonic. And again, update that for the whole list. And so what I'm going to do now is just the same as before. I'm going to plot my total again. So by inserting a scatter graph, we get something that looks like this. Quite a bit different. And what you can see here is hopefully an illustration of one of the ways you can recognize the presence of even harmonics. And I like to call this the mirror image. So what you can see here, if I put my sort of cursor on the 180-degree point, the halfway point in this waveform, you can see hopefully that the pattern that's formed by the waveform kind of has a mirror image in the second half. So we have this big peak here, it sort of tapers off, it goes negative, and then here's its mirror image. We get a small little bit of positive there, and then we get this tapering, and then that big peak, or that big sort of trough in its negative form, and then back to zero. So hopefully you can see that. You could almost imagine putting a mirror down that that center point there, and although this part is negative and that part's positive, it's not a perfect mirror image, but you get the idea. There's a kind of center point here, and there's a symmetry on both sides. Let's change back to the odd harmonics. Sorry, that was even harmonics. So I'm going to change that to the third harmonic again, and I'm going to change that to the fifth harmonic again. So if we update, we get back to the waveform we saw before. And here we have a pattern that repeats itself. You could think of this as a mirror image still, but you can see that the pattern repeats itself in the same order as in the second half as in the first half. Rather than it being a mirror image, we have this what's called a repeating pattern, as I like to call it. That's a little bit different. So I'll just make a note of these down here. So for even harmonics, we have what we call a mirror image. And for odd harmonics, we have a repeating pattern. So you can see here for the odd harmonics, the same kind of pattern takes place twice. It's repeated. Whereas in the mirror image, the pattern is reversed. Let's go back to the mirror image very quickly. Hopefully you'll be able to see the difference. So going from odd harmonics back to even, so the second and the fourth. So we're back to even harmonics now, and that's updated. And here we have our mirror image, which is very different to what we just saw. So it's very difficult to try and decipher these complex waves when they're presented to us. But one of the fortunate things in electrical engineering is harmonics usually only arise in odd or even. You'll either only get odd harmonics or mainly odd harmonics, or you'll only get even harmonics. It's generally one or the other. And harmonics come from a variety of sources. There's a range of reasons why harmonics come about, but it tends to be mostly odd harmonics or mostly even harmonics. And so by recognizing whether we have a case of odd or even harmonics just by using our two little rules here, the mirror image or the repeating pattern, it goes some way to narrowing down the source of the harmonics. So I hope this video has been useful, both in how to build up a complex wave using Microsoft Excel, but also how to recognize the presence of odd or even harmonics in a complex wave.